Welcome to the automotive use case of the REWIRE project. My name is Athanasios from KENOTOM, and together we will have a look at REWIRE's adaptive in-vehicle software and firmware patch management and software functions migration. Starting with the automotive use case motivation, currently within the automotive industry, the software updates are primarily done on-premise at a local dealership. This means that there is no option for constant over-the-air software updates, especially with respect to safety critical functions. Additionally, no current concept exists for critical functions continual operation, which means that in the case of an ECU compromise, the ECU degrades to a predefined safe state with no option to maintain its functionality. With current and future automotive trends such as autonomous vehicles and the connected vehicles and software-defined vehicles, there is an increased need for constant over-the-air software updates, as well as a need for assuring the continual operation of critical functions. The latter is of particular importance as more and more functions are grouped into less ECUs, which means that the potential ECU compromise can impact significantly increased vehicle functionality. Following with an overview of the automotive use case, we have identified three main areas that are needed from REWIRE. Firstly, the mitigation of cyber attacks that need to be detected and corresponding countermeasures need to be deployed, for example the migration of the ECU workload to another non-compromised ECU. Secondly, there is a need for a secure framework for over-the-air software updates, and finally secure communication between the vehicle and external entities, such as the OEM itself. On the figure on the right hand side, we can have a look at the automotive use case setup that consists of three boards. The one on the left is a Genesis 2 board and acts as a zonal or domain controller that incorporates the functionalities of the powertrain domain. The one at the bottom, the NVIDIA Drive or Dev Kit, acts as an ADAS ECU, while the third board, again a Genesis 2 board, acts as a zonal or domain controller for another vehicle domain, for example as a chassis or body control unit. For the connection between the devices, we have opted for Ethernet, which is strongly gaining momentum within the automotive industry. Having a deeper look at the automotive use case, we can see here the information exchange between the boards, as well as the primary software components on each board. Starting from the left hand side, we can see the ADAS controller that has a graphical user interface for interfacing with the driver or a higher level ADAS functionality. This component outputs what is the currently desired speed or position of the vehicle, with the ADAS component correspondingly handling the calculation of the required engine torque, braking, or steering. In the middle, we can see the Genesis board that holds a safety logic, which is basically the application of safety limits within the ADAS output, along with the corresponding vehicle sensing, actuation, and further calculations. The boards communicate over Ethernet using some IP, a middleware designed for integration with AUTOSAR, which is a reference automotive architecture. On the far right hand side, we can see the additional Genesis 2 board, which in theory would have another purpose within the vehicle. Within this board, the migration of functions will be demonstrated. For example, in the case of a compromise on the first Genesis 2 board, on top of the exemplary functions A and B running on the second ECU, the safety or vehicle services could also be executed. With this setup, the continuity of the operations will be assured between the ADAS and this second ECU. Having now a more general overview of the migration concept, we have identified two possible scenarios. In the case that the ECU undertaking the workload of the compromised ECU does have access to the underlying sensors and actuators, then we would have a continual operation of the ADAS function. In the case that no access to the sensors or actuators is possible, this concept will allow the execution of the fail-safe mechanisms of the compromised ECU on a clean and secure environment. For example, the fail-safe mechanism for driver alerts for this system malfunction due to the security breach. We will now proceed with a pre-recorded video of the entire setup, which is briefly highlighted here. We can see the two boards, Genesis and NVIDIA, along with the corresponding communication via Ethernet, the Genesis host PC, as well as the keyboard that provides the user input to the NVIDIA board and the NVIDIA monitor itself. As we can see here, the user activates the ADAS control functions, and using the arrow keys, the desired speed or steering angle is increasing, which is highlighted with the green graphs on the NVIDIA monitor. The white graphs show the actual speed and steering angle as it is communicated from the Genesis board. We can also now have a look at the NVIDIA GUI in higher resolution here, where the complete NVIDIA output can be seen. Again, with the pressing of the arrow buttons, the targeted values are changing, with the actual values measured from the Genesis board showing the actual state, which is increasing in a more smooth and limited manner as the internal safety limits from the Genesis 2 board are also applied. On the top of the screen, we can see further information, internal variables of the system, the steering and speed data, along with the user input. Finally, as a showcase of an exemplary attack, we have injected a security breach where a malicious attacker could modify the speed and toggle its value to a fixed 0 value. This can be seen here with a yellow marking of the speed value. This information could be mistakenly relayed to the driver, a scenario that showcases the need for continual monitoring and attack mitigation on the internal ECUs of the vehicle and the data exchange between in-vehicle and external networks. This video demonstrated that the entire business logic of safety-critical functions operates in its environment, representing at the moment the as-is case of the automotive domain. Our setup is now ready to receive the various technical developments and artifacts of REWIRE. Concluding with the next steps and the upcoming planning of the automotive use case, we have currently finalized the automotive demo, with some final refinements coming primarily for the GUI or any additional logic needed for showcasing the REWIRE mechanisms, for example a replication or imitation of a security attack. For our overall planning moving forwards, within the first experimentation period, the Genesis 2 software will be deployed on Keystone TE, while the User Story 1, the software update, the User Story 2, which is the attestation and risk management, will be further demonstrated. Within the second and final experimentation period, the third and fourth user stories will be demonstrated, which are the migration between the two Genesis boards and the onboarding into a collaborative vehicle network.